Hi everybody, this is counting and probability video number 14, and we are going to be talking about a number of things, among them including the idea of mutually exclusive and also the idea of OR events. So last time we did not, this time we're going to do OR, and we'll go from there. I'll create another slide and we'll start on that right post haste. So we want to start this out by defining what the word mutually exclusive means. So if I have any two events, A and B, and it is absolutely impossible for both of those events to occur at the same time, then they are called mutually exclusive. In other words, they exclude each other at the same time. Mutually means kind of together. So together they exclude each other. So they have nothing in common. That's what we call mutually exclusive. So a quick example of this would be, suppose I had the set A and the set A complement. Are those mutually exclusive? Yes or no? That's right. The answer is yes. These are mutually exclusive. Why are they mutually exclusive? Well, because A complement, or not A, has all the elements that are not in A, and A has all the elements that are not in the complement of A. Therefore, they're mutually exclusive. It's impossible for each one to occur at the same time. On a more practical note, what about the even and odd integers? Are those mutually exclusive? Yes, the answer is correct. Can an integer be both even and odd? And the answer is no. It cannot occur at the same time. So those are also mutually exclusive. Alright, I hope that gives you a good idea of what is or is not mutually exclusive. And we'll go to the next slide. So what we are given is a formula that says that the probability of mutually exclusive events is the probability of A or B, or if you wish, A union B. And that's just going to equal the probability of A plus the probability of B. You would just add those together. Okay, let's do a couple of examples and kind of flesh out this definition. So the first example we want to do is, given a deck of cards, we want to find the probability of drawing an ace or a jack. So once I say the word or, then I have to think about things being mutually exclusive. So is getting an ace included in getting a jack, or is getting a jack included in getting an ace? In other words, do they have anything in common? The answer is no. Jacks and aces do not have anything in common, therefore they're mutually exclusive. Therefore, this is equal to the probability of getting an ace plus the probability of getting a jack, which is going to equal 4 out of 52 cards plus 4 out of 52 cards, which is 8 out of 52, which is, I believe, 2/13 when you reduce it. And then you could use a calculator to make this a decimal if you wish. Any questions? Think you got it? So let's try a couple more. So why don't you give this problem a try? Probability of getting a red 2 or a black 5. Are they mutually exclusive? Yes, they are. A red 2 and a black 5 have nothing in common. How many red 2s are there in a card deck? Well, there are 2 of them. There's a diamond and a heart one. And how many black ones are there? Well, there's 2 of those as well. A spade and a club. And so there are 2 of those as well, so the probability of a red 2 is 2 out of 52. Black 5 is 2 out of 52. And so you add those together since they're mutually exclusive and get 4 out of 52, which reduces to 1 out of 13, which you can turn to a decimal. So if you think you've got this, what I want to talk about then is the idea of doing something like this. How about the probability of a red card or a jack? Now what's the problem with this? Can you think of it? That's right. These are not mutually exclusive. And why are they not mutually exclusive? Because there are some jacks that are red. So it turns out we need another formula for the case where they're not mutually exclusive. And it's very similar to the one we've done before. So since these overlap, what I have on the bottom of your slide in white right here is the formula that we use for not being mutually exclusive. And it says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And so what I want to do is I want to show you why this is true, and then we can go ahead and do this problem. And so here's how we're going to do it. We're going to draw a universal set with it, which is our sample space. In this case, the sample space is all cards in a deck. Okay? And what we know is that the number in the sample space is equal to 52. And now what we have is we have 2 sets. Here's one set. We're going to call this the red card set. And here's the other set. We're going to call this the jack set. And what we know is that there are 26 red cards and there are 4 jacks. But 2 of the jacks are red, so the number 2 goes here. Since there are 2 more jacks, the number 2 goes there. There's our 4 jacks. And since we have 26 red cards, we need a 24 here. So when you look at this in terms of a set, all of a sudden you can see that the number of red cards that we have, this right here, is equal to 26. The number of jacks we have, that one right there in the formula, is equal to 4. But what have we done if we take 26 plus 4? We have actually counted these 2 that are red jacks twice. So what you have to do is subtract it out. So what we're going to do is now we're going to do this problem. What's the probability of a red card or a jack? Well, it is equal to the probability of a red card plus the probability of a jack minus the probability of a card being red and and jack at the same time. And in that case, the probability of red cards, we know there are 26 and divided by 52 total cards, plus the probability of a jack, which is 4 divided by 52. But we need to subtract the overlap because we've counted it twice, and we know there are 2 red jacks, so that probability is 252. And when you do this, 26 plus 4 minus 2 is equal to 28 over 52, which is equal to 7/13 when you reduce it. And then you can write it as a decimal if you wish using a calculator. Any questions on that? So this is the new situation, and where it comes from is this little baby right here that we did in set theory when we were counting numbers. that helps us figure out where the overlap is. Any questions about that? Feel okay? Alright, I'm going to pause the video. Your homework will cover these ideas tomorrow. There'll be quite a bit to do, and we'll go at it from that point. Anyway, see ya.